Dear students, how are you? I hope everything is good there. So today, from today, we'll be starting our normal physics classes, and our class, as we know, we are not able to continue at school. That's why we have to depend on these notes, especially maybe in the PDF form or some web page and videos that I'll be sending to you. So to get the maximum benefit, what you have to do is you just go through the notes first, and after reading the notes, you come back to the video section again, because the video is just a part of the note that explains some terms or maybe some problems or some derivation. But I want you to focus more on the notes, because the notes are written according to the syllabus which have been revised recently by the council. And this time the syllabus is much lighter, much smaller in size, and I hope we can complete the syllabus in the right time if we continue our classes consistently. Okay, then let us go to the class right now. Alright, dear students, for class 12 today, I'll be starting from this optics. This is for 12. So in this unit, for today's class, we'll talk about this refraction of light, and this refractive index, after that we'll talk about total internal reflection, and after that the application of total internal reflection, that is in optical fiber. Okay, this will be the topics that we'll be discussing today. So let us see the first one, refraction of light. And as for the notes, you try to copy down from the link from the notes. I mean the note with the link that I'm posting in the WhatsApp group. And the notes are very important. All the syllabus, entire syllabus will be included in the note, so you don't have to avoid the note. Okay, then we'll see again this refraction here. In refraction, we need to have two different medium. The first one is rarer. It can be your air medium, and this will be your denser. It can be a water medium, for example. Then, if an incident ray falls on the surface obliquely, then this point will be the point of incidence, and through the point of incidence you need to draw a line, and this is what we call is the normal. This is the normal, and this will be your angle of incidence I. Then what happens is, instead of going along the straight path, the refracted ray or the other ray simply bends slightly here in this way. So this will be your angle of refraction. And what you observe here, this is the actual path of the light, but instead of traveling along the original path, it slightly bends. So this phenomenon is what we call as the refraction of light. Then here comes Snell's law. As I said, for the notes, you copy down from the web page that I have already sent by WhatsApp. And in Snell's law, what we have is sine of the angle of incidence here divided by sine of the angle of refraction. This ratio is equal to a constant. and this constant is nothing but your refractive index. This is what? Mu. So in short, if you write as mu here, suppose say the light in the figure, it is traveling from A, let us say medium A to medium B. So the starting medium is put here A, and the finishing medium is put here B, so that it becomes equivalent to sine of I divided by sine of R. So this equation is what we call as Snell's equation, or simply Snell's law. One of the most important law in refraction of light. Okay, actually there are two laws in refraction. The first law says that the incident ray, the normal and the refracted ray, all of them lie in the same plane. And the second law says that the ratio of sine of the angle of incidence to the sine of angle of refraction is equal to a constant. And this constant is known as the Referral Index here. So all these notes, as I said, you try to refer the PDF, or the web page that I have sent to you. Everything is there. This is just for the brief explanation. I cannot write everything here because the video will be too large in size, and I have difficulty in sending the videos to you again. Okay. After this, we'll be deriving this formula here. Mu is equal to, say, real depth divided by apparent depth here. It means the Referral Index can also be written as the ratio of real depth to apparent depth. Everything is there in the note again. I'm telling you one more time. There are so many ways of writing the Referral Index here. Referral Index mu can be written as C by V, where C stands for speed of light in air divided by speed of light in the given medium. You can write in this way, Referral Index. Or in terms of wavelength also, mu is equal to lambda 1 by lambda 2. So many ways of writing. So like that, the Referral Index also can be written as the ratio of real depth divided by apparent depth. What is this? I'll be explaining here. You just take a container here. The container has some water, let us say. This be the water surface. And here is the object. There's a incorrect. So this is the object here. Then if you take the ray of light coming from the object, which is falling on the surface at 90 degrees, then what happens? Nothing happens. It just goes straight. No refraction, no turning away. Alright, right now we'll try to derive this expression, that is Referral Index is equal to real depth divided by apparent depth here. This is equal to real depth divided by apparent depth. This is another way of writing the Referral Index. To prove this one, we'll consider this diagram. This is the container. Here is the water surface, and let us say this is the object here. If this is the object, then what if light comes from the object and it falls on the surface at 90 degrees? Then what, this simply goes straight, nothing happens. And if you take another point here, and this is the incident light falling at this point obliquely, then what, this will be your normal. Then what, this will suffer refraction. So looking from this line, if you extend this object will appear to be here, rising here, or this. So this will be your angle of incidence I. This is angle of refraction R here. So geometry says that this R and R, this should be the same. This I and this I also, it should be the same here. So you just call it as P, call it as Q. Then from the surface up to the bottom where the point O lies, this will be known as real depth. And from the surface up to the point where the object seems to be rising, this will be known as apparent depth here. Let this be called as the second medium, and this one is the first medium. So if you apply Snell's law says that referral index is equal to sine I divided by sine of R. Then the starting medium is 2 because the object lies in the denser medium. So you can write 2, it travels to the first medium, 1 here. Okay, then this is equal to sine I belongs to this right angle triangle OPQ. So if you apply sine I here, this is equal to perpendicular by hypotenuse. Perpendicular is PQ and the hypotenuse will be OP. Similarly, sine R belongs to this small triangle. Again, perpendicular is PQ divided by the hypotenuse is O dash P here. Okay, then you have this PQ divided by OP into O dash P divided by PQ. PQ cancel. Then you have O dash P divided by OP. Then O dash P can be written as O dash Q only when P and Q are very close. Now assume that this point P and Q are very close. Suppose a point P lies here, then O dash P will be approximately equivalent to O dash Q. So instead of this O dash P, you can write as O dash Q. Similarly, if this P and Q are very close, this OP can be replaced by OQ. So you can write OQ here. Since P and Q are close to each other, you can write. Then referral index 1 with respect to 2, this is still equal to O dash Q. O dash Q is nothing but your apparent depth divided by OQ. OQ, you can see this is nothing but your real depth, or interchange these two, referral index of second with respect to first, this is equal to real depth by apparent depth here. The reason why we put like this is that these two represents the denser medium. So always try to keep the denser medium at the bottom and keep the rarer medium at the top here. So this is your equation. So next we have total internal reflection of light. We'll see total internal reflection of light. In total internal reflection of light, we have two medium. One is the denser. This is the rarer here. Let's say first medium. This is the second medium here. Then you keep an object in the denser medium. That will be the object. And if the light is coming from the object and if it falls on the surface at 90 degrees, then nothing happens. It just travels straight. No refraction occurs. Then if you take a point here, then you can see this will be your line normal, and since it falls obliquely, this will undergo refraction. So this is your angle of incidence I, this is your angle of refraction R. Then if you take another case here, this is your normal again. You can see angle of incidence is increasing now, because as you compare these two angles, now this angle is greater right now. Then at this time, instead of traveling along this line, the refracted ray will be traveling along the surface here, such that the angle of refraction becomes 90 degrees. At that time, the angle of incidence will be known as critical angle C. And if you take another case here, what you observe, this is the same line normal, but in this case the angle of incidence is greater than critical angle. then what happens? The refracted ray just turns back in the same denser medium. So this phenomenon is what we call as total internal reflection of light. And do not forget that when the angle of refraction becomes 90 degree, here the angle of incidence will be known as critical angle here. This is your critical angle. Now let's see, in Snell's law, referral index is equal to sine I divided by sine of R here. You can see the light is traveling from second to the first medium. So let me write 2 to 1. Okay? Which is equal to sine I. Put the value of I here. I is equal to C. Then what sine R? R is equal to 90 degree here. So as you know, sine 90 is equal to 1. So we can write only sine C here. Okay? Or if you interchange these two, right? Interchange these two means that mu to 1, then what? This will be here, actually 1 is there in the denominator. So this can be written as 1 by sine C. Or in other words, mu is equal to 1 by sine C. It simply means that the referral index and the critical angle, these two are inversely proportional to each other. Okay, dear students, you please go through the notes. Everything is included in the note, and the class, this video, you just use it for explanation. And I hope that you can easily follow the notes that have been written. It was written in a very simple language, in a language that you can follow. Okay, then see you in the next class again.